I'm Dhanlakshmi. So here I'm there to discuss a topic which is related to advanced AI&ML. So that's matrix factorization. So let's see what's there in this topic. So basically, it involves breaking down a large matrix into smaller, simpler matrices that capture underlying patterns and relationships. So the advantage is that this method helps uncover hidden insights, reduce data dimensionality, and improve model performance. So singular value decomposition, matrix decomposition. SVD decomposes a matrix into three matrices. That is U, what sigma and V. Where U and V are orthogonal matrix, and the sigma is a diagonal matrix. So, a singular values, the diagonal elements of sigma represent the singular values capturing the importance of each dimension. So data insights, SVD provides valuable information about data relationships, enabling dimensionality reduction and noise removal. So non-negative matrix factorization, that is NMF. Non-negative negativity constant, NMF enforces non-negativity on both the input matrix and the resulting factor matrices. Part-based representation, it decomposes data into parts, providing interpretable insights and facilitating future extraction. So applications is that NFF is widely used in image analysis, text processing, and recommendation systems. So latent semantic analysis, in short, LSA. Document analysis, LSA analyzes the relation between document and terms, identifying the latent semantic relationships. So search engine, it improves search engine performance by capturing semantic meaning and relevance. Text similarity, LSA measures the similarity between documents based on their latent semantic content. So applications of matrix factorization is that recommending products and services based on user preferences and item attributes, reducing the number of dimensions in high dimensional data sets, simplifying data analysis and visualization. So extracting features from images and text data, leading to improved classification and clustering. So recommendation systems, user item interactions prediction model, personalized recommendation. User item interaction, so matrix factorization learns user preference and item features from historical data. So prediction model, it predicts user ratings or likelihood of interaction with unseen items. Personalized recommendations, the model suggests items based on individual preferences and potential interests. Image and text analysis, so feature extraction is the first, and content analysis, and feature extraction is that matrix factorization identifies meaningful features from images and text. So content analysis, it helps understand the content and relationships within images and text. Application is that example including image recognition and text summarization and topic modeling. So dimensionality reduction, data compression. Matrix factorization reduces the number of dimensions while preserving essential information. Visualization, it allows for easier visualization and underlying understanding of complex data sets. So improved performance is that lower dimensionality reduces computational costs and improves model efficiency. So the challenges and limitation is that data sparsity. Second is computational complexity. Thirdly, it is interpretability. Data sparsity is like handling missing values. So basically, if there are missed values, it's hard to identify patterns and also, and sparse data sets can be very challenging. Computational complexity. Matrix factorization can be computationally expensive, especially for large data sets. Interpretability. Interpreting the latent factors and their meaningful meanings can be difficult. So, in order to understand this concept much better, let's watch. So before getting into the video, you must know that single values equals square root of eigenvalues. Single vector equals normalized eigenvectors.
So this is a matrix
Basically,
square
it
root
is
of decomposition is an explanation for
so
eigen like a.
SVD is represented as the SVD decomposition is represented as A equals U into sigma into V. transpose. So A is the original matrix and U is the left singular matrix, and summation is the singular values matrix of diagonal matrix, and V is the right singular vectors matrix.
Sigma is singular. Only diagonal values are present. Rest of the values are zero. So the singular values that we will be calculating for a matrix, we will be placing them on the diagonal and write singular vectors matrix for V. Though you don't need to worry. I will be explaining you how all these are calculated. So starting off with SPD, this might be a bit tough on the mathematical side. So just pay attention. We will be first calculating A transpose cross A, and we will be calling both the matrix. Move the square root of already.
So singular values equals square underscore root of eigen values. So singular vector is equals normalized eigenvector. The decomposition is represented as A equals U into sigma into V transpose. So A is the original matrix, U is the left singular matrix, and sigma is the singular values matrix or diagonal matrix. So V is the right singular vector matrix. So it
So basically, in a diagonal matrix, as I've already explained,
so
only
it can
diagonal
be
values are present.
calculated as A transpose into A. So let's call this as A dash. So in order to calculate eigenvalues and eigenvectors for A dash, so as shown above in eigenvalue decomposition, calculate singular values for A dash using root of eigenvalues. These values will be used to form a sigma or a diagonal matrix. So calculate singular vectors for A dash by normalizing calculated eigenvectors.
Calculating the singular values for entity to get a sigma. Normalizing eigenvectors. So it is again, as you can understand, it is an extension of
Calculate eigenvalues and eigenvectors for A dash. So calculate singular values for A dash using root of eigenvalues. These values will be used to form sigma or a diagonal matrix. So calculate singular vectors for A dash by normalizing calculated vectors. So V equals a matrix of singular vectors of A dash. So
is
sigma
equal to
equals a
matrix
diagonal matrix with
of
distinct
singular vectors
values.
of A dash. Sigma is diagonal matrix with
In order to calculate U, we'll use the relation A equals U into sigma into V transpose. So A sigma transpose are known. You can be calculated by U equals A into V into sigma transpose. So this is a really nice example referring how SVD is calculated
the
with an
distinct
example.
singular values, and for u, for calculating u, the third remaining matrix, we can use this particular equation, because in this equation we have four variables: a equals to u cross sigma cross v transpose. We know a, we know sigma, we know v transpose. So eventually, using this particular equation, u equals to a cross v cross sigma transpose, and we will be placing all these three values, we will be getting a u also.
So that's all about this concept. I hope you understood much better. Thank you for watching this video.